so here we want to maximize and minimize x squared plus or x squared times y squared, subject to the constraint that x plus y is equal to 10. So just like we did before, we are going to solve this constraint for one variable, and we get y equals 10 minus x, and then we go and plug that solved constraint into our objective function. So we'll have x squared times 10 minus x quantity squared. Now we want to maximize and we want to minimize this particular objective function. So you could FOIL this out if you wanted to. Honestly, it's probably just going to be easier to plug it into the product rule. So at this point, once you have one function here, one variable, x squared minus 10 minus x quantity squared, now we are just going to apply our first derivative test to that function. So we are going to go into our product rule. We'll have our first function is x squared. Our second function is 10 minus x quantity squared. First function's derivative is 2x. Second function's derivative, we'll use the general power rule here. So we have 2 times 10 minus x to the first power and then multiply by the derivative of the inside. So we get negative 1. So that gives us negative 2 times 10 minus x. All right, so plugging into the product rule here, we will have 10 minus x quantity squared times 2x plus x squared times negative 2 times 10 minus x. All right, so we need to set this guy equal to 0. So it might be easiest to just say, as we always have, is there a GCF in these two terms? So when you look at those two terms, you do in fact have a 10 minus x common to both, and you also have a 2 common to both, and an x to the first common to both. So our GCF is 2x times the quantity 10 minus x. All right, so if we pull out the GCF, again, I'm going to divide by 2x times 10 minus x, divide by 2x times 10 minus x. These two x's cancel, the 10 minus x cancels here, and just leaves us with a 10 minus x to the first power. But again, we don't need to write this one power because there's nothing to distribute there. So from the first term, we get a 10 minus x. Now, from the second term, what we will have is a negative coming from the fact that this 2 and this 2 cancel, leaving us with just a negative. The x squared over x just leaves us with an x. And then the 10 minus x, those cancel out. So we're looking at 2x times 10 minus x, and then inside of this bracket, when we simplify, we get 10 minus 2x. And that is, again, our first derivative that we're setting equal to 0. Now, when you look at that first derivative, you say, okay, it's factored. So because it is factored, I'm going to set each of these factors equal to 0. And then solve. So when I solve here, I get x is equal to 0, x is equal to 10, and then from over here, add the 2x, divide by 2, and we get x is equal to 5. So there's actually quite a lot of contenders here for critical numbers, and you'll notice, or potential solutions I should say, and you'll notice that all of them are non-negative, so we cannot cross any out based on the fact that they're non-negative or not. So we're going to plug in the 0, 5, and 10, and we're going to plug in a number to the left and to the right into our derivative. All right, so if we plug in, let's say, now this is interesting here, okay? So you kind of look to the left of 0 and you say, oh, well, let me plug in a negative 1. But remember that our x value has to be non-negative. It has to be greater than or equal to 0. So it doesn't matter what this negative 1 evaluates to. All of this is not in our domain for the function. So really it's just 1, 2, 3 intervals that we need to plug in, okay? So you don't want to plug anything into the left of 0 because x has to be greater than or equal to 0. If I plug in, for example, 1 into the derivative, here, again, we're going to plug into each of the respective factors. So I have 2x times 10 minus x times 10 minus 2x that I'm plugging into. So this, when I plug in 1, will give us a positive. This factor will be 10 minus 1, so that will give us a positive 9. This factor will be 10 minus 2 times 1, so that will give us a positive 8. So each of those three factors are multiplying out or giving us a positive. All right, so then we plug in something between 5 and 10. So I might plug in, let's say 6. So that's going to give us a 2 times 6, which will give us a positive. And then 10 minus 6, which will give us a positive. 10 minus 2 times 6, which will give us negative. So that's evaluating to be a negative. And then we might plug in, let's say 11. So we'll have 2 times 11, 10 minus 11, and then 10 minus 2 times 11. So evaluating this out, we get a positive, a negative, a negative. So overall, we have a positive. So our first derivative test here is showing us that we are increasing until 5, decreasing between 5 and 10, and then increasing after 10. So looking at the structure of this, we see that we have a relative maximum at x is equal to 5, and we have a relative minimum at x is equal to 10. Okay, so that is our relative max. It's going to be maximized at x is equal to 5, minimized at x is equal to 10. Now, do remember though, it was two numbers. So what we have to say here is that our x plus y constraint is equal to 10. If x is equal to 5, then that means that our y value is also equal to 5. So if we go back to our constraint and solve for y, we're going to get that y is equal to 5. And the same thing goes here. If we go back to our constraint and plug in that x is equal to 10, then that means that our y is going to equal 0. So the corresponding y value we get from our constraint, and this would be y is equal to 0. So that's how we would write our answer. We would say that we're maximized, this function is maximized at x is equal to 5, y is equal to 5, and minimized when x is equal to 10, y is equal to 0.